I'm going to talk about SDR and the extent of continental lithosphere in oceans. You know that foundation of plate tectonics was discovery of linear magnetic anomalies in the oceans, and that supported the seafloor spreading interpretation. And an outcome of this discovery was the mapping of the boundaries between oceanic and continental lithosphere. And actually, the Northeast Atlantic Ocean with clear LMA was among the first case example. And here in the Reykjanes Basin, and also northward, the anomaly 24 gave an age for the continental bracket. But a simple fundamental question was not addressed. Is the accretion of new oceanic lithosphere the only geodynamic process capable of generating LMA, which will be symmetrical about divergence axis? And for me, the answer to this question is no. And it is a matter of SDR. So what are we talking about? SDR consists in bright seismic reflectors arched seaward, forming fan-shaped prisms, several kilometers in thickness. And they are part of the upper crust of volcanic passive or rifted margins. And they represent or are parallel to volcanic features such like lava flows and seals. And clearly, to my knowledge, they are associated with the stretching and thinning of the continental lithosphere when the mantle partially melts during extension. Since hence, the nature and structure of SDR and volcanic margins is better constrained from both seismic, direct observations and drilling. And when can be distinguished at VPMs are inner SDR, which are in the proximal and necking zone of volcanic margins, passive margins, and two other classes, types of features which are away from this crustal fin point, which is at the edge of the necking zone of the margin, and which are the outer SDR, so distal and seaward this crustal fin point, and the flat tying flows, which are usually more distal and also, of course, seaward the crustal fin point. The inner SDR, well, are for me well known, well, at least better understood, and there are some many congruent observations for them. I base myself mainly on the only exposed, fully exposed inner SDR worldwide, which is the Svartanek SDR, West Greenland, which is which shows the wool volcanic sequences from the bottom with yellow clastites and pillow lavas, and up to the more differentiated magma to the top. The dipping of the lava is to the southwest here, and this is a cross section. This is a view close to the main fault here, which is the sorry for the name, after Arthur Schwarzschild fought in Inuit. And what we can observe is on this SDR, we had the program on it for several years. And it is that the setting is purely continental. It is completely syntectonic and bounded by a this major normal fault, which dips continentward. The lavas are tectonized. They are made of both compound and thick flows, intruded by seals and dikes. The wedge, which is up to 5 and more kilometers in thickness, is up to 99.9% in volume magmatic, meaning no sediments or some metals. And there is here a clear correlation between the degree of mantle melting and the beta ratio, that is crustal thinning. Okay, we have some lots of geophysical data and geochemical data on this SDR, which are still not published due to some confidential issue with oil company, but there will be. Okay. The distal outer SDR and flattening floor are much more enigmatic, although some observations can be made. Some of those observations may come from the Lakshmi Basin, which is an aborted system of volcanic margins, and which is a very good illustration of what happens at the beginning of the onset of those pairs of conjugate of passive margins, volcanic passive margins. Notably, it illustrates well this concept that we first modeled and then observed of C block, explaining, well, a C block is just the common footwall for those detachment faults which dip continentward on both sides of those volcanic passive margin systems. And it may or not last for a long time, but during the margin development, but here it may be observed. And if you look to outer SDR, we see that you have inner SDR, outer SDR, the C block here on one side, coming from this line. And you may see that the outer SDR, and this is a common observation elsewhere, do tap down to a subhorizontal surface. So, yes. And you see also this kind of propagating like system, well, towards the C block. We can also look to those South Atlantic volcanic margins that we studied also for a while, and because they provide very high resolution observation for the deep crusts and upper crust of those of a very long area with volcanic passive margins. And that, as observed in Lakshmi, the end of outer SDR and the flat-lying flow, yes, sorry, I didn't focus on that, but if you look to this line here, you see that those outer SDR, their extremity is the top of a lower crust, which has all the properties of an injected continental crust. And if we look here to the South Atlantic margin, we have exactly the same. That is, we have a tapping down of the outer SDR onto this lower crust, which has high velocity, but whose velocity are not different from those from the lower crust, which is beneath the inner SDR and at the necking zone of the margin. So for us, this can be explained by the fact that this lower crust is an exhumed continental lower crust, which is far away from the necking zone of the margins. And if we look in more detail to those flight-line flows here, they appear to make to unlap the outer edge of the outermost outer SDR. You know, there is, like if you had here, the post-trip section is here, so that this is syntectonic, and you may observe this unlapping of those sediments or flows onto the outer edge of the SDR. And downward and deeper, you may see this brittle and injected deep layer that has been observed by other teams, which is in continuity with this subhorizontal or low dipping reflector system or of the beneath the outer SDR and continuing down continentward to the proximal part of the margin. So that we think that it is exhumed middle to lower crust, continental crust.
You're just past 11 minutes now, okay, Laurent?
Yes, okay. And so in a way similar, and this kind of, we suggest that this exhumation is in a way passive, meaning that it is driven mostly by gravity, and it has some similarities with what we observe at continental core complexes. And the point is that both inner SDR and in a lesser way outer SDR, both inner SDR and outer SDR generate linear magnetic anomalies. Inner SDR generate very high amplitude and wide magnetic anomalies, and outer SDR, and also in a lesser extent flat-lying flows, do generate oceanic-like magnetic anomalies. And this is just the consequence of the process of the exhumation process, because if you detach the C block from the margin, you create a space that is infilled by the outer SDR. And of course, the younger basalts are here and the oldest are here. And if you do that on both sides, you will get some pairs of linear magnetic anomalies. Okay. And if I apply that to the Northeast Atlantic, and if I look to these very nice refraction lines and with magnetic anomalies mapped on the top, and you can see in the seismic reflection line, which is related to that the very nice, very clear oceanic type magnetic anomalies in the Northeast Atlantic, close to Greenland, are top of outer SDR and flat-lying flows. And to finish, if I just, and this up to anomaly 21, and if I just map the Atlantic, the oceanic lithosphere from this observation, and given this hypothesis of exhumed continental crust beneath outer SDR is correct, then you reduce the surface of oceanic lithosphere in the Northeast Atlantic of about 25%. And now, if you consider that in between Greenland and Faroe, you have a bathymetric ridge, Greenland, Iceland, Faroe ridge, that includes Iceland. And actually, you have nearly a continuous set of SDR. And from Greenland to Iceland, and also from Europe, Faroe Islands to Iceland, and flat-lying flows also. And if you look to Iceland also, to the eastern and western part of Iceland, you have SDR. Very nice one here, and also here, everywhere. And actually, and contrary to what was thought before, they are fault banded. So to conclude, oceanic type lithosphere cannot be proven by the mapping of LMA only. And I think that there is a need for differentiating SDRs like SDR type LMA from oceanic spreading LMA. And this is ongoing work we do here. And also, of course, we have to explore if seafloor, while slow spreading seafloor spread, sea accretion process could give rise to SDR, like in Palmason's and Buck model. Thank you.
Merci, Laurent, that was wonderful. Are there any questions from the general audience? I know some of the conveners have questions already. If you have a question, you can write it into the chat or you can put your hand up. While we're waiting, Gwen Perron-Vidic has a question I will ask because her dentist prevents her from talking today. And her question is, have you ever observed onshore or offshore the feeder structure of these SDRs?
Observe, I can't hear very well because sorry, just have to.
I can repeat the question. Have you ever observed, either onshore or offshore, the feeder structures of these SDRs?
Okay. Yes, onshore, yes, completely. And this is a point I'm not on which I don't agree with Roger Buck. SDRs are not fed by their extremities. Actually, and this is observed also in Iceland. In the active system of Iceland, you feed SDR through the hanging wall of the fault system. And there is some magma which goes through the faults, the bounding faults themselves, and we observe that along East Greenland, but usually it is a very differentiated magma, often acidic magma. But the mafic magma comes from dikes which are, which don't form very narrow dike swarms. They are widely distributed at the hanging wall of the monocline.
There is a hand up. There's also a number of questions in the chat. I will perhaps ask Valentin Rim to ask their question, and then after that, if you could answer the questions in the chat, that would be great. So Valentin, if you could unmute yourself and ask your question.
Yep. Can you hear me?
Yes.
Okay, thank you very much for this very interesting presentation. I have a question for you. You presented this sea block. Do you also see this sea block in the South Atlantic? Because you also published seismic data from the Southern Atlantic. There it seems to be less clear than in the Laxami Basin to see where this sea block is.
Yeah, absolutely. But because it is a very mature system, so we think that we observe remnants of sea block at the necking zones of some of the margins. But the other location where we observed a sea block, and actually we were able more or less to map it, is in the Afar system. You know, and we had this recent paper made by wrote down by François Chauvet, And François, well, we did a very, we were able to map very precisely, well, I would say, flow by flow, the SDRs from Yemen to Ethiopia, well, Djibouti actually, and we think from those data that we had at the beginning of this opening, this alpha opening, you had a very wide C block actually, because we have similar in age inner SDR both along the Great Escarpment of Yemen and from Ethiopia. You know, okay, so it was very wide. And now we just have a remnant. The present day Danakil block is a remnant of this very wide SDR. So we can imagine that with time of this C block, with time the C block dislocates and become part of each margin.
Thank you.